So for Chapter 4, Section 3.1 in Introduction to Electrodynamics, we are talking about electric displacement. So electric displacement is actually called D. I'm just going to write it already and skip all the introduction. So D is equals to the electric displacement. Now, I'd like to think as the electric displacement as just the electric field, with a little exception. So, for example, I want to use the example that is given by the book. So, example 4.4, in which we have a wire surrounded by a uh, dielectric. I guess that's what it's called. By rubber insulation. Okay, that's the better way of calling it. And we are calculating the electric field at a point in between. So let's say a point right here. So we're gonna draw another Gaussian surface of cylinder with height is equals to S, and of course, well, the height here is gonna be equals to A. Therefore, A is greater than S. The length of this cylinder inside is gonna be equals to capital L, and the charge, of course, is gonna be equals to lambda. Okay, so if, for example, we were to find what is the electric field of a of this without an insulation, we will simply do that it's equals to the integral of the electric field over dA is equals to the charge enclosed. Now the charge enclosed is equals to enclosed is equals to our charge per length times our length, of course, and then E over dA. In this case, we would have to find the area of the surface of this cylinder. So we would have to find that is equals to the absolute value of absolute value of E times 2 pi A times L. So therefore is equals to lambda L. We cancel out the lambda on both sides, and we obtain that E is equals to lambda is equals to 2 pi, lambda over 2 pi A. Oh, actually, sorry, the height was S, no, not A, S, 2 pi S. And if we want to make it a vector, we just have to say that E is equals to lambda over 2 pi S in the S hat direction. Now, it's the same exact thing for D, because, okay, when we have this cylinder, we're actually going to have another electric field given by the polarization. So these two electric fields will add each other together, and so actually what I'm going to call D is equals to the electric E naught times the electric field times our plus our polarization. Why are we multiplying the electric field times E naught? Well, because when we're calculating the electric field, it's like we're calculating over a empty space, so there's no insulation. While instead P already takes into account the insulation of our problem. So if we just call it like this, or if we're actually to call it perfectly, we'd have to say that is equals to E naught times E plus P, the integral of this over dA is equals to the charge enclosed again, so we just said is equals to already lambda L. And we said that this part here now is called D, so we'll just call it D over dA is equals to lambda L. So what is this going to be equals to? It's going to be equals to the absolute value of D times, so 2 pi S capital L times YL. We cancel L on both sides, and we get the absolute value of D is equals to lambda over 2 pi S. And therefore, the factorial form of D is going to be equals to lambda over 2 pi S in the S hat direction. As you can see, it's the same formula that we found for our value right here. They're pretty much they're the exact same thing. That's why I wanted to use the example immediately. I think it really shows the power of this. One thing we can also say is that outside instead of this cylinder, so for example, if we had a cylinder that is bigger than, bigger but same length, no, that's not what I want to do, okay. Okay, so same length, always L. I want to say that in this case, this is S. So just a simple bigger cylinder, larger cylinder with now S greater than A, then we know now that there's no electric field induced by the polarization. So in our case, oops, oh sorry, here I actually forgot. Here I actually forgot a will be 1 over epsilon naught. So 1 over epsilon naught, and here's epsilon naught at the bottom. My bad. Okay. So now we said, well, we'll see that d, which is equals to epsilon naught times E plus P. In this case, there's no polarization, like we said, so P is equals to 0. Therefore, if we do the same thing, I'm just going to keep D just to make things more intriguing. Times dA is equals to charge enclosed, so we said L lambda L. So in this case, we're going to get the absolute value of D times 2 pi S capital L is equals to pi capital L. So we cancel the capital L's, and we get that absolute value of D is equals to lambda over 2 pi S. And if we want to, of course, make it as a vector, we would say that a vector of D is equals to lambda over 2 pi S in the S hat direction. But why did I say this value over here? Well, we know that now D is equals to this. So I can just substitute it, and we get that is equals to epsilon naught times E vector, of course, equals to lambda over 2 pi S hat. And of course, we get that the electric field is equals to lambda over 2 pi epsilon naught S hat over S. I like to write it this way. So as you can see, it all comes back together to our initial equation. It is pretty straightforward. The book goes in a little more into detail. I don't think you need exactly all that detail, but because as long as you understand what I'm saying here, as long as you understand actually the example, it is very much straightforward, very easy.